Hello friends, welcome to this channel. This is G Solutions, where we find solutions for your needs. Okay, today let us know the concept of this three-phase system. Previous video we already discussed the polyphase system. The polyphase system is actually made up of two or more single phase system. Now, if we mean three-phase system, we deal only with three single phase system, and we are studying this because this system is the mostly used or the commonly used system in the electrical industry. And the single phase system that is placed on one system, the single phase there are the same, but it is actually with a displacement of 120 electrical degree apart. Since that our N here is equals to 3, to be able for us to have a displacement, an equal angle displacement of this single phase system, our whole system is operating at 360 degree. Now, if you divide this by 3, it will give us 120 degree. So your phases are displaced at 120 electrical degree. So in representation, a waveform representation here, for instance, this is your V sub A sinusoidal waveform. Let us just assume that this is perfect sinusoidal waveform, and this is V sub A. Now, the other voltage, which is V sub B, okay, will start after 120 electrical degree. So if this is 0 degree, and the half of the cycle here is 180 degree, and the whole cycle is 360 degree. Or in radian, we use here pi, and here is 2 pi. Okay. Therefore, the middle or the median of this sinusoidal waveform will have 180 divided by 2 electrical degree, or 90 degree, or pi over 2. And for this one, for the negative cycle, we have here 180 plus 90 degree, that is 270 degree, or 3 pi over 2 for our radian. Okay. So if that is displaced 120 electrical degree, so this is 90, and plus 10 degree, that's 100, plus another. Maybe this is the point where the B sub B, or the other phase, will start. So the waveform will travel here, and when it hit this point, it will start now. The waveform for another phase will start. I represent it into a broken line. Okay, maybe to just distinguish it to the other phase. So these are the broken line, and let us name this as B sub B. Okay, so now as the degree goes higher, so 120 degree, 140 degree, okay, 150, 160, 180, okay, and then after that, again 120 degree plus 120 degree, that is 240, and from here 180, maybe it's 200 here, and when it hits 240, okay, the phase waveform will start for the other phase. Okay, so it may be here. Okay, so this is the representation. Okay, this is for B sub C. This is the representation of your three-phase system. And actually, you can also use phasor representation. So we have here in XY plane, and the first one that appear first is B sub A. So that is your reference, B sub A. And when it hit 120 electrical degree, so B sub B will start. So B sub B will be here because it lags B sub A. So this is B sub B, and the angle here is 120 degree. And the after that B sub B started, and again it turned to another degree and hit 120 electrical degree again here. Okay, so this is B sub C. Okay, and by the way, for this is again 120 electrical degree, and this is 120 electrical degree. Okay, by the way, the vector rotation, is from this point to this one, referring to the clock that will be a counterclockwise rotation. Okay, so this will be the vector rotation. Okay, BC. Okay, the vector rotation. So this is how you represent a three-phase system. And for the connection, if we are to connect your phases into a star connection, or we call it as a Y connected system, this one, for instance, this is your B sub P, this is B sub P, B sub P, okay, and here is your B sub L, and this is your IL, this is your IP. Again, your IP, your current in phase, is the same as your line current, and your B line here is actually twice the phase voltages, because P plus P, that will be VP sine 180 degree over N. Since that our N in a three-phase system is equals to 3, we place that 3. Okay, so now if you have your calculator with you, so you know that 180 is divided by 3, that is 60 degree. So for further simplification, you have twice BP sine 60 degree. Okay, and if you are to get the value of sine 60 degree, I do hope you see this calculator. So again, for our sine 60, the value is 0.866, and you multiply that by 2. This is 0.866, and you multiply this one by 2, and it will give you 1.732 BP. Okay, so VL is actually 1.732 BP. Actually, this one is that is the square root of 3. Okay, if you are going to take the square root of 3, this is actually equivalent to 1.732. Okay, therefore b sub L is equals to the square root of 3 b sub p. Okay, so this is in the Y connection. How about in delta connection? So we connect again your coil to delta and investigate your variables. So this is again your B phi, B sub P, B sub P, the phase voltages, and what flows here is your IP, the phase current, and here is your I line, the line current, and here is your B sub L. Okay, so you'll notice that here what is equal are the voltage. So the phase voltage is equal to the line voltage, and the current here is actually twice IP at a certain angle. Okay, therefore your line current is twice IP sine, that is 180 degree over N, but our N here is 3 since we are in three-phase system. So therefore, again, if you are going to get the value of this one, that is 0.866, like this one, because this is 60 degree, sine 60 degree. And then 0.866 is multiplied to 2, it will give us 1.732 I sub P. Okay, this is your line current. And 1.732 is actually square root of 3 I sub P. Therefore, I sub L is equal to the square root of 3 I sub P. So this is all about the three-phase system in which our source or load can be connected in Y connection or delta connection. Okay, so thank you so much for watching this video, and I hope that you will share, like, and subscribe on this channel. Thank you so much.